Well, let us illustrate this result with a Cobb-Douglas function. Okay. A and the alpha i's are positive constant, as you know. And we computed the cost function. This was the cost function. And the cost function, as you see, is differentiable. So this result applies. So if we want the optimal solution set, we just need to differentiate. Let me introduce some notation. So the optimal solution set of our cost minimization problem we are going to call it capital X of XYP. This is a parametric optimization problem. It depends on two parameters, P and Y. Okay, so for every pair PY or YP, we have a problem, and I called XYP the optimal solution set. So this is a set valued mapping from R plus cross R plus plus N set valued into R plus N. And it's called the input demand correspondence. Okay? Then, input demand correspondent, because of course I am the producer, I know that the prices are P, I have no influence on prices. My desired output level is Y, so I need inputs, and this will be my demand for inputs. These are my optimal inputs, the ones that allow me to produce at least Y, which I want, at a minimum cost. Okay, so this is why it's called the input demand correspondence. Is this terminology clear? In some cases, as when the cost function is differentiable, this is just a singleton. So this set has only one element. In this case, we have a function, not a set valued mapping. And it is called the input demand function. Okay, so what we know, what this is saying is that if this is differentiable, then little x of yp is well defined because the solution is unique and coincides with the gradient of C as a function of prices at P. Let us check this with this example. Let us compute just one component, the jth component of the demand function. Because the demand function is the gradient of the cost function, this is the jth partial derivative of the cost function. So I just take derivative of this with respect to Pj. So all remains the same except the jth factor here, in which I will have to, the exponent will change. Okay, so for the jth factor, alpha j divided by alpha will come out as a factor, and then I will get this to the power, this minus 1, and then using the chain rule, this multiplied by 1 over alpha I, which removes the alpha y that came out. Okay, so at the end we get also this alpha coming out removes this alpha. So in the end we get y over alpha one over alpha, and then because of the minus 1, this comes, so I prefer to write it slightly differently. So I have to divide by pi over alpha I, so I get alpha, but it's alpha j. Ah, no, but it cancels out with this one, sorry. So let me see. This alpha I, yes, it cancels out. So the derivative would be alpha j over alpha pj alpha j alpha I divided by alpha minus 1 times 1 over alpha j. This cancel out, and this one will cancel out with this one. But I will get still, because of the minus 1, this dividing, which means multiplying in the opposite ordering. So what I get is alpha j y divided by a 1 over alpha 1 divided by pj times this product. Is this correct? Well, if this is correct, this should coincide with what we got when we computed the cost function. I mean, to compute the cost function, this cost function, we have to solve the cost minimization problem. And then we found the optimal solution, which, if there is no mistake here, was this one. Okay, well, this shows how a strong relationship between the gradients in the differentiability case and the optimal solution of the cost minimization problem. This is not a practical way of solving the problem because, I mean, we obtain it very easily, but we first needed to compute the cost function. And computing the cost function involved solving the problem. So this is only useful for theoretical purposes. It's not a practical method of solving the cost minimization problem unless by some miracle you know the cost function. Okay? Is everything clear? So now we are going to study the properties of the Jacobian matrix of a differentiable input demand function. So our assumption now is that little x is well defined, so the optimal solution set is a singleton. There is a unique optimal solution to the cost minimization problem. And we assume that this function x is differentiable. As a function of P, of prices. So, what can we say about its Jacobian matrix? We have that x of yp is the gradient of C at P. So take Jacobian in both sides. So the Jacobian of x of yp is the Jacobian of the gradient. And what is the Jacobian of the gradient? We are taking derivative of the derivative. It's the second derivative, in this case, the Hessian matrix. Okay? And this is very interesting because the cost function, as a function of prices, is superlinear. It is concave. Then the Hessian matrix of a concave function is positive semi-definite. Negative semi-definite. Okay, it's concave. Negative semi-definite. Then, conclusion. Maybe unexpected. I mean, it's expected because of this, but if we didn't know Shepard's lemma, I could not suspect that the Jacobian matrix of the input demand function is negative semi-definite. And this has some consequences. Not only negative semi-definite, but if this is of class C2, then, so which means, assuming that X is of class C1, okay, then this is of class C2, then it's also symmetric. For a C2 function, the Hessian matrix is symmetric. What are the entries of this Jacobian matrix? Partial derivative of xi with respect to pj. By symmetry, this means this is equal to the partial derivative of xj with respect to pi. It's very interesting, and to me, I'm not an economist, to me surprising. This means, probably speaking, that the influence of a change in the price of input j on the demand for input I is the same as a change in the price of input I for the demand of input j. A nice consequence of Shepard lemma, so it gives some results with some economic meaning.
Could you please repeat that last line in terms of input?
The sentence.
Yes.
This partial derivative expresses the dependence of xi on pj. So a derivative tells us what a change in pj would mean in xi, in the change of xi. If the price of input j is changing, this tells us what would be the impact of this change in the demand for input I. And here is the same, but reversing the roles. So this impact is the same as in the opposite direction. The same as the impact that a change in the price of input I would have on the demand of input j. Is this obvious from an economic point of view? Not to me, but I am an economist. If some of you have some intuition, I would be glad to hear. Okay. Another result which you may think, well, this is not surprising at all. Then, if you tell me this, you will be surprised in a couple of days. A negative semi-definite matrix has non-positive diagonal elements. The diagonal elements are these. They are all less than or equal to 0, which means it's a negative semi-definite matrix. The diagonal elements are non-positive. What does it mean? That xi depends in a non-increasing way on pi, which means that if the price of an input increases, the demand for that input decreases. This is very reasonable, but in this context it holds, but not always. In this context, always. But in consumer theory, we will see, this is very well known by economists, and I will give you examples that will convince you, that sometimes when the demand of a good increases, we buy more of that good. I mean, when the price increases, it becomes more expensive. Then I will buy more. When this does not happen, I mean, when you have this situation, when the price increases, the demand decreases, in consumer theory, this is called the law of demand. But the law of demand, as many other laws, is not always fulfilled. In consumer theory. In production theory, yes, as we have just seen. I will give you examples. Sorry?
Apple products, generally the prices is high, but still people are always getting by.
Apples may be a good example, I don't know. But the point is, today apples are more expensive than yesterday. Then I will buy more apples. This is what I will show you that it may happen for a rational consumer. You don't need to be crazy to eat more apples when they are more expensive. Sorry?
So for me, that is a crazy consumer if the demand.
No.
Prices are increasing and we are buying more.
You will do it sometimes in your life, and I don't think you are crazy.
We do with this with branded clothes.
No, but this is a matter of preferences. This is a matter, okay, oh, this is very luxurious, I will be very prestigious if I wear these clothes, etc. No, it's not this. Okay, I mean, I should not have mentioned this now because it belongs to consumer theory and it's not yet the time. In fact, it will be one of the last days when I will give you examples. But this, what I am telling you, is very well known, and every consumer, rational consumer, not a crazy consumer, sometimes, depending on his or her preferences, but with very reasonable preferences, very reasonable, this situation may happen. If you are very curious, then I can tell you now, but no, I want to use my technique of motivating you are attending the next class. Okay, so I will not tell you the solution now, but I think I will succeed to convince everybody, including you, that this is not irrational, okay, not crazy. Okay? But here, you are satisfied, no problem. The price of an input increases, then the demand for that input decreases. What else can we say? Let me use matrix notation for a moment. Instead of P inner product X, I will write P transpose X of YP. Okay? So everything is a column vector and T denotes transpose. So this is the inner product. Can you tell me what is this equal to? This is the inner product, this is the cost of X of YP, and the price is P. But X of YP is the optimal. So this is equal to the optimal cost. And the optimal cost is what we call C of YP. Okay? Well, so from this equality, take derivatives. We have here a product, so we get P plus, we get X of YP plus P transpose. I'm taking derivatives with respect to P plus P transpose the Jacobian of X equal the gradient of C of Y at P. Do you agree? Just using calculus rules. And this gradient is x of yp. Shepard lemma. The input demand function is the gradient of the cost function. So in this equality, these two terms cancel out. So we get P transpose Jx of y P is equal to 0. Agreed? So look, this is a vector equality. P transpose is a row. This is a square matrix. The product is a row vector. So it's equal to 0. But what does it say about the Jacobian matrix? I can put this here. In fact, the correct notation here would be this one. So, the other one is not incorrect, but it's a little bit of abuse of notation. So, what can we say about this matrix? You have a square matrix which multiplied with a non-zero vector gives 0. So this matrix is singular. Okay? If this were non-singular, then the only solution to this equation would be P equals 0. So the Jacobian matrix of the input demand function is singular. It has no inverse, its determinant is equal to 0. Something for which I don't have any economic interpretation. Okay? I don't know if economists have. Any question? Okay, now I told you that I will not be all my life dealing with Cobb-Douglas functions, that I will use some others occasionally. Now it is time to consider Leontief production functions. Let me motivate the introduction of these production functions with an example. Suppose we are producing, let's say, a fertilizer by mixing together 3 different chemical products in the following proportions. From 2 liters of chemical A, 1 liter of chemical B, and C liters of chemical C, I produce 8 liters by mixing them of our fertilizer. Suppose I have 300 liters of A, 80 liters of one, and 200 liters of C. How many liters of fertilizers can I produce? Hmm? 1800. I don't know. How did you reply so quickly? Exactly, 40 liters. So you are a too efficient producer. So every producer of fertilizers will hire you as an engineer to. Okay, no. I mean, because I have 300 liters of A, and I need 2 liters of A to produce 8 liters of. So, with this I could only produce 50, 150. But the same with B, but I have too little of C. Okay, so only 40. Of the other chemical products, I have too much, which I'm not going to use. Okay? So the general situation, so in fact the solution was minimum, well, in fact, no, in fact I will produce 320. Yes.
He can have 8 liters of
Yeah.
in that ratio, 1:5, right?
Yes. So the solution is not 40, it's 320. I mean, if with 2 I can produce 8, with 300 over 2 I can produce 150 times 8. And the same with the others. So, let's say this is 1 barrel, okay? So I can produce 40 barrels, which means 320 liters. Okay, but the conclusion was I needed to take the minimum This gave us the number of 40 barrels that we are able to produce, or 320 liters. Well, this is in general, we would have an input. A1, AN will play the role of 215 in the example. So I need to use in these proportions to produce 1 unit of output. Then when the inputs I use are x1, xn, the production function is the minimum of x1 over a1 xn over an. So this is a very reasonable production function. It's a very clear economic interpretation, it's natural. And this is the so-called Leontief production function. In the lecture by Professor Misra, he considered a more general class, which is this function to the power alpha. Of course, this can be done. I never have seen this, but this makes full sense. But it was the first time I saw this exponent alpha there. So we can use it also here, but I mean, let us use the classical Leontief production function. So, by the way, this production function is very nice. A nice production function should be quasi-concave, non-decreasing, and upper semi-continuous. This is not only quasi-concave, it is concave. These functions are linear, then concave, and the minimum, in the same way as the maximum of a collection of convex functions is convex, the minimum of a collection of concave functions is concave. Not only concave, even superlinear. It's positively homogeneous of degree 1. Then it is clearly non-decreasing. If the xi increase, then the value of the function increases. And it's not only upper semi-continuous, but continuous. So it's very nice. With the Cobb-Douglas functions, we suffered a little bit when making the computations for the cost function. We are not going to suffer at all in this case. It's very simple. So, what is the cost function? No, this is the condition because now this is our production function. So we have to minimize Pixi subject to the minimum xi over ai greater than or equal to y. But this is the same as saying xi divided by ai greater than or equal to y for every I. Okay? The minimum greater than I is the same as saying every one is greater than I. So we have xi greater than or equal to ai y. So there is only one constraint for each variable in which no other variable appears. And we are minimizing this sum, so we can minimize separately each term. So the optimal solution is when we have equality here. Okay, so the optimal solution is xi equal aiy for every I, which means the optimal cost is the sum of pi aiy, which is y times the inner product of p with a. So this is the cost function corresponding to this Leontief production function. Of course, it satisfies all the properties we saw of cost functions. And the cost function happens to be differentiable at P. So Shepard lemma applies. Shepard lemma says that x of yp is the gradient of C as a function of prices at P. So the ith component of this demand function is the ith. Sorry, I made a mistake here. There is no x. There is a. Okay? Okay, this is what we obtain. Right? X would make no sense in that situation. So the a derivative with respect to p, with respect to pi, so this is the partial derivative of c with respect to pi at yp. The partial derivative of this sum is ai times y, as we had seen. This is the optimal solution we found of the cost minimization problem, which we needed to compute the cost function. I insist it's not a practical way of finding the input demand function, but we check with this example the validity of Shepard's lemma. Also, because this function is regular, we should be able to recover it from the cost function. Let's see if this is the case. So let's compute the maximum over y in R plus of those i's for which C of yp is less than or equal to px for every p. This is the formula that allows us to compute a production function inducing this cost function. But we know that this production function, x is given, will coincide with the original one if the original one is regular, which is the case now. Okay? Then, okay, let's make the computation in this particular case. This is YPA. So let's solve this maximization problem. Well, Pi is strictly positive, so this condition means y less than or equal to Px divided by Pa. So I need to find the largest y, which is less than or equal to this expression for every p. Okay, so this is the largest lower bound of this expression, so it's the infimum. So the optimal y would be the infimum over p in R plus plus n of px over PA. Can you compute this infimum? I will tell you what you can do. First of all, observe that this objective function, the variable is p, is positively homogeneous of degree 0. If you multiply p with lambda, then lambda and lambda disappear. It's positively homogeneous of degree 0. This means if you normalize by adding the extra constraint Ex Ep equal 1, nothing changes. Do you agree? I mean, if you have whatever p you like, then you compute the value of the objective function at this p. Very good, but I don't like your p. I want only p's that satisfies this inequality. Then what do I do? Instead of your p, I consider your p divided by EP. Then if I replace p here and there with my p, then I obtain the same value. But this vector I have considered satisfies that constraint. So this means the value this objective function takes in the whole space, in the whole orphan, are the same as it takes here. No need to go beyond this hyperplane to find the optimal solution. Okay? This is one thing. Second thing, I can replace R++ with R+. Now, because I added this constraint. Okay? Why? Because of continuity. Sorry, this is A. Because of continuity. But thanks to this constraint, P cannot be 0. So this denominator does not vanish. Here I forgot to say, but it's obvious that the parameters defining the Leontief production function are all strictly positive. Well, and now, how can you solve this problem? Once you have formulated it like this. So we are minimizing on this triangle, okay, because this is R plus n intersection this hyperplane. So the constraints are P sub I non-negative and sum of Pi equal 1. This is a set of this type. This is a polytope. Actually, the infimum is a minimum because it's compact and the objective function is continuous. But what do we know about this objective function? Does it have any nice property? Linear over linear. That's fantastic. Convex, concave, whatever you like, convex, concave. but I like here convex. And I like here concave. Concave and positive, of course. So convex over concave, we proved that this is quasi-convex. I don't like this. So instead of looking at this as convex and the other as concave, I like at this as concave and this one as convex. Okay? This is the right way of looking at it. Then this function is quasi-concave. And one can easily prove, if you want I will prove it, that a quasi-concave function attains its minimum on a compact convex set on an extreme point, on a vertex. Okay? Do you agree? If you want, I will try to prove it later. It's quasi-concave. Then I only have to look at the vertices. And there are 1, 2, 3, in general, n vertices. The vertices are the unit vectors. So I only have to consider the values that this function takes at the unit vectors. And at vector ei, the numerator is xi. And at vector ei, the denominator is ai. So this is the Leontief production function. We knew that we should be able to recover it, okay, from the cost function, because this Leontief production function has all the nice properties that a production function should have. Did you know this result, that a quasi-concave function attains a minimum at least one vertex?
For convex, it is fine. So by how we prove for convex, we can use it for
I mean, the same idea you use for the maximum of a convex function or the minimum of a concave function, you can use for the quasi. Because
usually when we take any point of this polyhedral, so it will be some linear combination, so we can always less than inequality and then we take the maximum in the case of convex and then we got.
yes, what is a quasi-convex function? Can you tell me without telling me the inequality and without talking about convexity of level sets?
The value will be, all the value will be less than at the corner points.
A quasi-convex function is a function that on every segment attains the maximum at some endpoint, at one of the two endpoints. Okay, then using this idea, it's immediate. In fact, and this is quasi-convex. For quasi-concave, you have to change signs. But then, in fact, this is a characterization of quasi-convexity. I mean, this, not what I said, but this. So a function is quasi-convex, and it follows immediately for what I said, if and only if on every compact convex set, it's attained its maximum at some extreme point. Maybe another points too. But at least one extreme point is an optimal solution. This is if and only if. You accepted that because a segment is a particular case of a compact convex set. I mean, you accepted, I said, do you want to prove? You said no. Because you accepted that every quasi-concave function has a maximum on a compact convex set on an extreme point. Now suppose you have a function which on every convex compact set has a maximum at some extreme point. In particular, this will hold for a segment. And this condition for a segment is exactly quasi-concavity. For a quasi-concave, I'm not sure I'm saying things properly. For quasi-concave, you have to minimize. For quasi-convex, you have to maximize. Okay. Thank you.
How
But
to change the inner product over the whole Rn plus, then to the polyhedral, and then we use the condition for the quasi-convexity over the like the bounded polyhedral.
yeah. Well, I have done it, but I'm sure I'm not the first. I have not seen in any other book, so I produced this proof, but I am sure you can find it in many places. I am not.
This thing is beautiful.
So it's the first beautiful thing you see in this course.
I like it because I thought that I can use it.
You needed to waste almost 1 week to find something beautiful in this presentation. Okay. Okay. I forgot something, but okay, we'll do it later. Before Leontiev, I wanted to explain something else about Cobb-Douglas, but now I'm happy that I put Leontiev first because you liked it. So we will go back to Cobb-Douglas this afternoon, and then we will finish with production. We have been producing too much. Now it will be the time to consume. Okay?